Welcome to this video. This video we will look at what is diffusion models. Diffusion models are a class of generative AI models that have revolutionized the field of image synthesis, video generation and even text to image applications. In this video, we will look at what are diffusion models, how the diffusion models works, what are the different popular diffusion models, and finally we will discuss some of the applications of diffusion models. First, we will look at what are diffusion models. Diffusion models are a class of generative models that have gained popularity in generative AI for their ability to create high quality data such as images, videos, and audio. These models are based on a stochastic process called diffusion, which involves incrementally corrupting the data and then learning to reverse the process to generate new samples. Diffusion models generate new data by first introducing noise to existing data and then training a model to reverse the process, that enabling the creation of data similar to the original input. Diffusion models have established a distinct and important position in the expensive field of generative modeling. Their growing popularity is no coincidence. It stems from several key characteristics that make them especially valuable in the realm of generative AI. One of the standout advantages of diffusion model is their ability to generate images of expectational quality, particularly at high resolutions. These models produce intricate and consistent visuals, often surpassing other generative techniques in terms of visual fidelity. How the diffusion model works? Diffusion models work by systematically transferring data into noise and then learning how to reverse this transformation to generate new and meaningful data. This approach leverages probabilistic modeling and deep learning to create realistic outputs. Forward process. In this step, a clean data point is progressively noised over several steps until it becomes pure noise. This process is modeled as a Markov chain where each step adds a small amount of noise. The original data is progressively corrupted by Gaussian noise through a series of steps. At each step, a small amount of noise is added. After all steps, the data becomes almost indistinguishable from pure Gaussian noise. Gaussian noise is a type of a statistical noise that follows a Gaussian distribution. It is a common assumption in signal processing, data analysis, and machine learning due to its simplicity and its frequent occurrence in real world scenarios. Reverse process. In this process, learn to undo the correction by iteratively predicting the cleaner version of the image to reconstruct the original image. It is parameterized by neural network. It will start from the random noise, then the model generates the data by progressively refining it. Noise scheduling in the context of diffusion model refer to the strategy used to control how much noise is added to the data at each step during the forward diffusion process. The noise schedule defines the variance or relative terms across all time steps, which directly influence the model's ability to learn and perform the reverse diffusion process effectively. Each step, a variance, determines the amount of noise added to the data. Minor corruption preserving more details of the original data. Significant corruption pushing the data closer to pure noise. Cumulative noise defines how much total noise has been added up to step. It often expressed in terms of the mean scale factor. A well-designed noise scheduling ensures that the model can effectively learn noise removal at all levels of corruption. Also avoids overlay difficulty learning tasks such as denoising from highly corrupted state. Linear schedule, Gaussian schedule, exponential schedule, custom schedules, these are the commonly used noise schedules. The schedule determines how noise level vary across times. A good schedule balances low noise level early on for learning fine-grained features, high noise level later for the robustness to heavily corrupted data. Noise schedules affect how well the reverse process reconstruct clean data. Pure schedule can result in blurry or unrealistic samples. A careful chosen schedule can reduce the number of reverse steps needed while maintaining quality. Empirical studies guide the selection of schedules based on the specific task and datasets. Linear schedules are simple and effective for most general purpose applications. Gaussian schedule often outperform other in terms of sample quality for image generation tasks. Training a diffusion model involves teaching a neural network to predict the added noise or denoise data corrupted by Gaussian noise. This enables the model to reverse the noise process and generate realistic data such as image, text, or audio. Training process involves data sampling, noising the data, noise prediction, loss computation, and gradient update. The choice of the noise schedule play a crucial role in determining training stability and the quality of generated samples. UNet is the most widely used architecture in diffusion models. It leverages skip connections to efficiently learn multi-scale features, enabling better performance and faster convergence. Atom is the most commonly used optimizer in diffusion models. For application like text to image generation, conditioning inputs guide the denoising process. These inputs ensure that the generated output aligns with the specified conditions or prompts. Training a diffusion models is computationally intensive, require extensive resources. This includes access to large dataset and high performance GPUs to handle the significant training time and complexity. The main challenges in training a diffusion models are high computational cost, hyperparameter sensitivity, balancing noise level. Training diffusion models demands extensive computational resource due to the need for multiple forward and reverse passes across large dataset. High performance hardware such as GPUs or TPUs is often necessary to manage the computational load efficiently. Training success heavily depends on the careful tuning of hyperparameters, including noise schedule, learning rate, neural network architecture. Improper tuning can lead to suboptimal performance or instability during training. Ensuring the network performance consistently across all noise level is a critical challenge. An imbalance may result in poor denoising quality or incomplete data generation, especially for extreme noise conditions. Generation in diffusion models utilizing the trained model to create new data samples by reversing the forward diffusion process. The process begins with a random noise sample representing the most degraded state of the data. The model applies a sequence of denoise steps, progressively refining the noise sample. At each step, the model predicts and removes the noise, gradually revealing the underlying structure of the target sample. After completing all denoising steps, the model produces a fully structured and realistic data sample. The output aligns with the pattern and characteristic learned during the training, make it resemble data from original dataset. The reverse diffusion process is the core of how those models generate high quality, coherent output across various applications from image to audio and beyond. Sampling speed, mode collapse, complexity in conditional models are the challenges in generation with diffusion models. Standard reverse diffusion process involves hundreds of denoising steps, making generation computationally expensive and slow. Techniques like denoising diffusion impact models help reduce the number of sampling steps, improving efficiency without significantly comprehending output quality. Achieving diversity in generated outputs can be challenging for certain noise schedules. This issue may result in model producing limited variations, which reduces its overall generative robustness. Conditional generations, such as text to image tasks, required balancing two critical aspects: fidelity to conditioning input, that ensuring the generated output align closely with the provided prompt or condition. Realism, it maintaining the overall quality and coherence of generated sample. Striking this balance can be challenging, particularly when the conditioning input is highly specific or abstract. Next, we will discuss some of the popular diffusion models. Diffusion models have gained significant popularity in the field of generative AI due to their ability to generate high quality images, audio, and other data types. Some of the diffusion models are denoising diffusion probabilistic models, DALI 2, Imagen, stable diffusion, latent diffusion models. Denoising diffusion probabilistic models are one of the foundational framework for diffusion models. They work by gradually adding noise to data and then learning to reverse the process to generate new samples. The key features of these models are iterative denoising process and high quality image generation. DALI 2 is a diffusion based model that generates images from textual description. It builds on success of original DALI. Use a diffusion process for improved image quality. The key features of this model is high fidelity image generation and the ability to edit and modify existing images based on text prompts. Stable diffusion is a latent diffusion model that operates in a lower dimensional latent space, making it computationally efficient. It will generate high resolution images from text prompt. Main applications are text to image generation, art creation, and photo editing. Imagen is a text to image diffusion model developed by Google Research. It leverages large language models to understand text prompts and generate corresponding images. Key features are high quality and photorealistic images, also strong alignment between text and generated images. Latent diffusion models operate in a compressed latent space, making them more efficient than models that work directly in pixel space. The key features are reduced computational requirements and a high quality output with fewer resources. Next, we will look at applications of diffusion models. Image generation, image editing and enhancement, video synthesis, audio generation, 3D modeling and rendering, medical imaging, data augmentation, scientific research, anomaly detection, creative writing and content generation, gaming and entertainment. These are some of the applications of diffusion models. In the field of image and video generation, they power advanced tools like DALI 2 and Stable Diffusion that enabling text to image synthesis, realistic image enhancement, and video editing. They assist artists and designers in creating unique artworks and helping improve the image quality through super resolution and in painting techniques. In video synthesis, they facilitate text to video generation, predictive frame rendering, and seamless video modification that revolutionizing digital content creation. Beyond visual media, diffusion models contribute significantly to audio generation, producing music, realistic speech synthesis, and sound effect for entertainment and virtual assistants. In 3D modeling and rendering, they generate lifelike 3D objects, reconstruct scenes, and enhance virtual and augmented reality experiences. Their application extend into medical imaging, MRI and CT scan clarity, generating the synthetic medical data for research and aid in anomaly detection for early diagnosis. Scientific research diffusion models are instrumental in molecular design for drug discovery, climate pattern simulation, and the enhancement of astronomical imagery. They also contribute significantly to data augmentation by creating diverse dataset which boost the performance of machine learning models and facilitate domain adoption. Furthermore, those models improve anomaly detection in areas such as industrial inspection, fraud prevention, and healthcare monitoring. In this video, we covered what are diffusion models, how diffusion models works, what are the popular diffusion models, and some of the applications of diffusion model. I hope everyone understood this session. If you have any question, please put them in the comment section below. Thanks for watching.